Disappear.
Okay. We do that coming to Europe. Yeah. It's the yeah. Yeah. No, that's good. That's good. Yeah.
Use the microphone. Speaker. CVPR doesn't
I understand. I didn't understand why it took him so long. Yeah.
I think you also had some discussions with
Yeah. We should so finish this project.
Yeah. This come first and do master next.
Yeah. Yeah.
Your is set. Yeah. Okay. I think we can do that. Yeah, because of this.
Language speaker basically covered program. We use the audio system errors.
We see. So maybe there is a software that simply the slides. Okay, let me do that. So send your link.
Yeah.
It doesn't take time around.
Yeah.
You have my email.
Yeah.
No,
I remember
they did not.
we were speaking.
Okay.
Okay.
Let's take a look
Yeah.
I can help you set up.
Oh yeah. Let me. Do you have an HDMI?
Yeah.
Yeah. I'll just yeah.
This is for the audio, so the the microphone. I mean. Yeah. So when you screen sharing, it will record your audio for the microphone. Yeah.
Right, so we are continuing with Professor Felix Heide, talking on scalable autonomous driving via fully data-driven simulation. Felix is a professor of computer science at Princeton, leading the Princeton Computational Imaging Lab, and the head of AI at Torque Robotics, building full autonomous stacks for self-driving trucks, and also a dear friend. He had also founded the startup Algolux, and his group at Princeton explores imaging and vision approaches that allow computers to see and understand what still seems invisible for humans today. It's very great to have you here today, Felix. Welcome. The stage is yours. We're all ears.
Thank you so much. Fully data-driven that we want to talk about. Let me go over our AV stack, which is illustrated here on the top, separated into a perception, prediction, and planning module. It's a fully modularized stack, and this is done by design so that we can actually use this modular structure to learn in an end-to-end fashion where individual modules are forming each other with well-defined interfaces instead of having a chance to bypass some of that information and ignore these individual modules. And learning is used in all stages at Torque, independent of whether that is a neural network that's in a particular module or a conventional algorithm that we make differentiable with differentiable proxies that we cannot come up with a differentiable form of that algorithm. And then ultimately we treat the entire stack like one big perception outputs of the multi-sensor fusion and learned prediction outputs that are learned in an end-to-end fashion by supervising the stack with a planning objective. So again, showing you here that a natural output of this end-to-end training is really robust perception if you have a modularized stack. This stack hinges on a long-range multimodal BEV feature stack. On the right side, you see such a BEV representation. And in a tracking environment, you have to solve a little bit more than conventional BEV perception tasks because of the vibration that you have in a tracking scenario. You also need to solve online collaboration along with the perception itself. So let us look at this multimodal BEV module in a little bit more detail. We rely on a multimodal model that operates directly on raw image data, LiDAR data, radar data to make predictions in BEV space. And if you look at the camera branch here, we use raw data in a different way than it may be used to other stacks and actually propagate gradients all the way back to the ISP as one example of a conventional algorithmic block that you typically wouldn't tune. Why does this matter? This ultimately matters because we need to see at these ultra long distances of beyond a kilometer in range to make long-term strategic planning decisions. So our task is fundamentally different than what robotaxi models that you see deployed in Waymo or Tesla have to handle. So most of our ODD is highway driving, where we have a truck with almost double the braking distance at 65 miles per hour, going from 90 meters to 160 meters. The top shows you an urban scenario with blue seats. And you have to embrace this on a low-level embedded design too, for two reasons. So let's look at a dense BEV model that you may be used to from your favorite AV stack. And you see that the number of features required to store and operate on actually grows quadratically as we increase distance. On the right side, we see our Sparse bird's eye view feature stack, which goes just linearly, which allows us to do long-range perception on the GPUs before the NVIDIA Thor architecture line. And this is important to be able to do long-range perception, but also to have the inference time down enough so that we can actually have the chance to do RL-based training. Here's the architecture of our Sparse BEV stack, one level deeper. The model independently encodes images and point clouds fuses them in sparse voxel space lifted into 3D. So to overcome the quadratic memory of the dense representation, we develop a fully sparse architecture based on sparse voxels that ultimately represents only the occupied regions and hence reduces the memory space. And it does attention in this sparse space too, using a multi-scale sparse voxel grid to capture both fine details and large-scale context efficiently. To allow for this very efficient inference that I'm showing you here, this is a bird's eye view fusion stack at full resolution of all of our cameras, LiDAR sensors, and radar. And this works robustly across multiple sensors in real time on a single NVIDIA Orin at long ranges of up to 1 kilometer. In the prediction and planning stage, in order to learn from it, we also rely on fully learned prediction and planning modules. This is essential to allow us for plans that are robust to high ambiguity that multiple futures have. And planning takes this into account. And our planners, our learned planners run alongside an analytical planner layout here, which provides safety constraints that in an EVM style fashion use as constraints to operate and make the best plan and come up with the best plan using our learned models that are highly efficient during inference time that fits inside the safety constraints. So let's just look at prediction for a second. To predict multiple future trajectories of multiple agents, use an autoregressive transformer where we model one set of agents per time step, and then we model the entire scene as a set of sets, where we have one set per agents and then a set of sets per the entire scene. And this allows us to use attention both in social sense, so agents can attend to each other, and they can attend over time. Then with the help of learnable seed parameters, we can predict the modes of the most likeliest possible futures that we can attend to them in real time in our planning style. So in order to provide enough diverse data for learning by self-play, use exponential tilting offline reinforcement fashion. So let's look at a log recording that I'm showing you here on the top left. If we take this log recording and we exponentially tilt the learned return distribution, we can turn the scenario into an adversarial scenario, where the other agent here, shown pretty small, is encroaching on our particular lane and actually adversarially crashing into our reloading code. Here's another example, which is an uneventful drive turned into a tilted scenario. And these scenarios are essential to challenge our AV planner in the validation and in the training phase, because we need to see scenarios that are ultra rare, such as a an extreme cut-in scenario that I'm simulating on the bottom right here, or a pedestrian crossing where a pedestrian is crossing over a highway, which is extremely rare and an edge case in our training. So again, as mentioned, treating the entire stack as one big neural network, conceptually that we can pass gradients through to the learned components or trained parameters of the conventional algorithmic blocks is essential for our training methodology to work. So working with the modular stack, we directly inform, as mentioned at the beginning, components that are deeper in the stack by an upstream objective. So for example, we fix tracking persistency, ID switches by training a prediction and planning stack. Or the key to make this end-to-end paradigm work is really a lot of sensor data, so we can perform this end-to-end training. So sensor data that's sitting at the input of our stack that we want to train. And in order to make this work, we built a physically grounded world simulator that I want to go over quickly. So here I'm showing you diverse generated physically grounded training and validation examples. We rely on this data from, we can rely on this data from a safety perspective because it is physically grounded. I'll show you a little bit why that is. And we can allow for multimodal simulations, which are essential to learn consistent predictions across the stack, across all sensors. So going one step back, the high-level goal is to move away from this traditional development cycle where we have one real world. We have a number of tracks that we acquire data in that is limiting that our output data for the recorded events that we acquire and limited by the number of trucks that we have. We have a massive amount of data that we need to store and analyze, and there's no feedback loop with respect to the actions to the real world. So the idea is to move towards a stack as follows, where we have scenarios that we can retarget into an infinite amount of virtual scenes with retargeted actors and behaviors. The one that I showed you before on the previous slide, just for camera images. And this allows for them closed loop training, where an action has effect on the other actors and ultimately the virtual sensor data that we capture. We can do closed loop end-to-end training with this approach, which is computational costly, but something that is essential to our approach. So how does this work? Use a radiance field-based scene representation. There's a lot of work at CVPR that goes into detail on this for our radiance that we use to generate image content, and then a surface-based representation plus radiance sitting on top of the surface, on top of the surface geometry to simulate our LiDAR measurements. So images are then rendered with a given camera pose and calibration, and LiDAR point clouds are ray traced by each beam. And the cool thing is that these both representations can inform each other. The radiance field sits on top of the proxy geometry and informs the proxy geometry and vice versa. So here's a static scene with its own 3D representation decomposed in geometry and radiance. And then you can render this from ego or from an arbitrary camera position within the scene box. You see this radiance representation. So this is obviously limited to the bounds of the scene. So then model the far range and background environment with an environment map that we can use for lighting. And we model all of the dynamic objects with individual learned 3D representations. We then compose the scene as a scene graph with the relative actor locations and orientations at each time step. And this fundamentally allows us then to simulate trajectories by counting for the transformations over time and generate renderings of images and LiDAR at arbitrary time steps. So let's look at camera outputs first. I'm showing you an original scene that on the right side, we retarget with an additional actor decomposed from another scene to get pretty good photorealistic outputs of these scenes. Here I'm showing you a scenario on the left side driving up to an intersection. And on the right side, you see highly wavy trajectory of the ego to simulate erratic control behavior that the planner has to compensate for. You can insert new actors. So let's look at this scenario where we drive up to an intersection. And on the right side, we start with the same scene. And we insert a bunch of new actors, which is this car coming in a number of times. Here's an interesting scene where I'm showing you the leaving vehicle, this white vehicle that's just leaving the scene, swerving as it leaves the scene, driving aggressively away, which is important for everything. So these camera renderings are obviously not enough. We have a multimodal stack. So here I'm showing you a multimodal scene with both multi-camera and LiDAR simulation outputs. And next, I'm showing you here a crash scenario of the same scene with the vehicle in front as the ego enters an on-ramp and the vehicle does a hard brake. And so we crash into it. So a scenario that we don't want to capture and acquire in your real-world data. Here's another multimodal input scene driving towards the overpass. And you also see that the stack directly provides us with pseudo-label data too that we can use as a separate training data set to initialize our stack. I just training perception at the beginning. And here we see a simulated crash scenario. the original. Here's a crash scenario where we have a wrong way driver approaching our vehicle. And again, something you don't really want to capture in the real world. Finally, here's a scene with a pedestrian. Yeah, perfect. And here's the same scene simulated with a pedestrian, initially occluded from the vehicle, running in front of our vehicle. So rapidly approaching our vehicle and actually colliding with the vehicle. I'm going to play this once more so you can see this. So again, last second, the pedestrian in yellow is colliding with our vehicle. Okay, so let us look at this in isolation for a second and evaluate on generated training data. So let's pick a standard perception module of the Fusion stack that we add generated data to in addition to real world data. So this goes even for perception, just beyond the conventional augmentation approaches. It can simulate realistic occlusions or very dense actor scenarios. So here I'm showing you the results with an off-the-shelf model, and we see that in all cases, this dramatically improves performance, and this is evaluated on real-world data that was manually labeled, just in isolation to validate the perception module itself. So as a physically grounded stack, we can already directly expand into other modalities, and here I'm showing you work on radar fields that we presented at last SIGGRAPH. You can use a similar surface representation. And in this particular case, you use a 2D radar and get 3D information out of it. Okay, so for the rest of the talk, I'm going to go into the interesting meat here, the behaviors in our world model that you saw in the previous slides, already simulated. We learned those actually in a fully data-driven. So let's take one step back and ask us what happens if we just take offline data, log recordings. Then we have data that does not react to the actions of our AV, and we only see the data that we actually have recorded. So we embrace offline reinforcement learning for the behavior simulation part. So this is a return conditioned autoregressive transformer that we use for closed loop behavior simulation. And we enable steering the actor behaviors by exponentially tilting of the learned return distributor. And this allows us then to simulate adversarial scenarios such as vehicles colliding with each other, changing the goals of the individual agents, as well as letting them drive offline. So since last year, we extended controls, and which is the name of the work here that we use to also model behaviors of multiple agent types, such as vehicles, pedestrians, and cyclists. And with this approach, we can simulate all the agents of the scene that I'm showing you here, or choose only to simulate a few specific ones. You can see that we can comfortably handle large scenes with an exploding number of agents, each having their own respective goal. Our agents all are aware of each other and able to interact with each other. And we can automatically generate an almost infinite variety of long-tailed scenarios here, just the behaviors. But argue that this is still not enough, because we fundamentally are limited to existing initial scenarios that are either manually handcrafted or recorded. And so fundamentally, I'd argue that we need a data-driven simulator to really make reinforcement learning. So if you look at existing data-driven simulators, they really only offer a very narrow slice of all the possible conditions as simulation environments are, again, either manually handcrafted or field or contriving. So let's look at Waymo's Waymax simulator. This really only contains about 2,000 kilometers of unique roadway, which is a fraction of the 20,000 kilometers an average human driver drives per year. So to solve this problem, we propose to train a generative AI model that we call Scenario Dreamer. And the code of this was linked with the QR code at the beginning of the slide to synthesize novel simulation environments, which can then expose our planet to a potentially infinite variety of interesting and diverse scenarios, which is the key thing here to make it work. So as a fully data-driven simulator, we train it on large-scale publicly available data sets, such as Plan or Waymo, can condition on known scenes, or other conditioning inputs. And the key thing is that we find that a fully vectorized processing approach, a vectorized diffusion method, is key to make it make the processing and learning effective and high performance. The video on the right side shows a scenario Dreamer synthesized scenario where the learned planner is depicted in red and the surrounding actors are in blue. And this scenario is fully generated by a scenario Dreamer and execute that in closed loop. So we support a few different modes. The first one is, let's say you have a map or existing map condition, then we can do map condition object generation. So we can place the objects shown on the right side in a learned approach in realistic positions. We can generate the entire scene, expose the actors as well as the roadways, which is what I'm showing you here in the middle. And we can do a scene and painting. So we can take an existing tile and continue it by in-painting. And for each of these videos here, I'm showing you here the reverse diffusion chain output by a scenario Dreamer. So here I'm showing you examples of simulations generated by Scenario Dreamer, where the AV planner under tests is shown here in red. And we can see that Scenario Dreamer can generate this endless variety of diverse and realistic simulations that I mentioned before. Okay, so how does it work? So we decompose the task of generating simulation environments into two individual subtasks. The first one is initial scene generation, which includes the initial ego position, surrounding actors, the underlying map, expressed as a set of centerline vectors. And then the second one is behavior simulation, where we auto-regressively simulate the actors forward in time in a closed loop and reactive. And we use controls for that, which I described just a little bit before. And then what we do is we specifically model the joint distribution over the simulation environments as a product of the initial scene distribution, which is a distribution over the initial agent positions as 0, the map M with optional conditioning, for example, on the city that we would like to sample from, and then the behavior simulation, which is the distribution over the future actor positions conditioned on the initial scene conditions. And the key thing is that we model the initial scene as well as the behaviors all in a data-driven approach, which is critical that we can actually learn realistic scenarios. So here's the architecture in more detail. The scene generator is a transformer-based latent diffusion model that looks as follows, right? So we embed each vectorized element, so the centerline vector, object state vector, and the lane connectivity graph A into a latent space with a VAE, where we then process each of these vectorized elements through a sequence of factorized lane to object, and object to object attention vectors. Once the VAE is trained, we then train a latent diffusion model to sample from the VAE's latent distribution. And novel scenes are sampled by sampling from the LDM to generate a set of latents, which are then decoded with the VAE decoder. During inference time, we perform a set of diffusion steps and then decode to finally get the produced scene, which we roll out with control set. The Scenario Dreamer's initial scene generates a 64 by 64 tile. And then by doing in-painting, we can simulate virtually unlimited lengths of scenarios. Here I'm showing you 500-meter routes generated by Scenario Dreamer, where we successfully apply diffusion in painting, where the ego driving through this entire scene is highlighted in red. So To compare this, we trained two models, a 400 million parameter base model and a large, about 700 million parameter model that we compare on Waymo and NewPlan. And you can see that we outperform the baselines such as Sledge on map generation and agent generation that we measure on these data sets. And the important thing is by doing this vectorized diffusion approach, we're actually using 2 times fewer parameters, and we're using 10 times less GPU hours to generate these simulations. Qualitatively, when we compare to Sledge for a random sample of initial scenes, you can see that Scenario Dreamer generates much more high fidelity and more realistic lane topologies and initial agent configurations, with much fewer overlaps here while sampling about 3 times faster. Okay, so finally, let's use Scenario Dreamer for RL plan. This is really challenge an RL planner more than Waymo scenarios. When we train a PPO planner, the favorite algorithm by almost anyone in this case here, for RL policy training, we do this in GPU drive on 100 Waymo scenes, and then which are processed in a Scenario Dreamer compatible format, then evaluate this planner on real scenarios and synthetic scenarios generated by Scenario Dreamer. So for a route length of about 55 meters, which is the average length of Waymo scenarios, we can see that we have relatively similar planner failure rates, which shows that we only have a small distribution shift between real and generated scenes. But when we increase the route length to 100 meters, we can see that we can challenge the planner significantly and observe a 50% increase in collision rates. And when we use adversarial tilted agents for behavior scenarios, for behavior simulation, we see an additional 12% increase in collision rates. So this shows us that Scenario Dreamer is an exciting method for evaluating and challenging AV planners. You can obviously imagine that you then even tilt the scenario generation itself. But just generating longer ones is already a major challenge. So in summary, I've hopefully convinced you of the exciting opportunities of generative methods for end-to-end training, validation, and challenging of RL planners. I believe this is truly the missing piece to make AV scalable beyond super costly iterative flow deployments. I'd like to thank you all.
Thanks a lot, Felix, for the amazing talk. Other questions from the audience? Yes, please. You can go to the mic.
Thanks for your talk. You talked about this photorealistic simulator and then this scene dreamer. How do you think of the two together or separately? Because like you train end to end, then you want camera data, but then you have this like arbitrary scene data. Do you have to create photorealistic scenes for these arbitrary?
Yeah. So it's a great question. So that's an active area that we're working with. Right. So the obvious answer is so right now these two components are separated, right? So I can't quite combine the scene generation fully with the end-to-end approach. It goes all the way to the behaviors, right? But I can only generate the behaviors for existing scenes that I've captured but retargeted. So one active field that we're working on is then take initial Scenario Dreamer maps, generate a full 3D scene, right? That you then can use as a physically grounded initialization to generate also the sensor data. So you need to generate the entire 3D scene in order to really completely test it.
How do you think about the compute required for that end-to-end simulation versus the scale you could do with this just scene dreamer?
Yeah. Exactly. So that's why if you just look at behaviors and planning, right, this is already working, right? So there we have fast enough inference, so we can actually make it work, right? We need to see a lot of samples to really truly make our work, right? So for the end-to-end piece, you can do this in stages, right? So you can train if you have a modular set, you can train the end-to-end piece of the perception itself, right? And then combine this and treat this in a fine-tuning set. Right, so first train them separated and then combine them. Otherwise, the compute will explode.
I also had a question about the sim.
Yeah.
You talked a lot about like the simulation working, the photorealistic simulation working for multimodal sensors like LiDAR, radar, and camera. What are like the shortcomings? Where does it fail?
Yeah, so I think the one of the really exciting active areas is harsh weather simulations, right? So this is also where some of the sensor simulation work that you also see at CVPR is going towards, okay, how can we take existing radiance fields and simulate realistic adversarial scenarios such as rain, fog, snow, and how we can make them realistic for multimodal sensor. That is still something that, but you have the same issue actually with conventional rendering engine-based simulations. This is not very straightforward. But learned models for this would be really exciting.
Thank you.
Yeah, there was already a question in the back. Maybe you want to, like, I'm referring to the lady, yes? Okay, yeah, you can take it first. I think
Thanks, Felix. Very impressive presentation and results. I have a question about the camera LiDAR simulation data augmentation programs. So, how do you generate those scenarios to create augmented data sets? Is it heuristic-based or using some scenario generation models?
Yeah, great question. So these were generated with a high number of actors. So just as a quick litmus test, right? So what is happening? What are in our training distribution and the training data set that we had the cases that are relatively rare. And if you look at the average distribution of highway driving, the density of the scenario, the density of the actors is not very high, unless if you're in a traffic jam, right? There's not a lot of stuff happening. And if you're in a traffic jam, the vehicles are not moving. So one of the easy things to do is just populate the scene with a lot of actors, so which is something that you pretty much never see. Populate it also with a lot of pedestrians and other scenarios. So just by skewing it like that, you already get a massive gain. It's just an example of where the simulation can actually help you to dramatically augment your existing training data.
So thanks a lot. Maybe another question. So, what's your comments or your thoughts about the recent video generation models? You think we can also generate very realistic.
Yeah. Great question. So ultimately, so we use these video generation model as a supervision way to simulate our physics grounded base models. But ultimately, you cannot get away of the physically grounded models because we found that you always have some artifacts or issues that the model is fundamentally overfit to. And you will quickly see this, right? So take an existing off-the-shelf model and try to train on it, right? Even if you have some layout conditioning, this will unfortunately not work because you always have a distribution shift. You always create these artifacts, right? And then it becomes even more iffy if you want to train a prediction and planning stack on top of it, right? Where you want to have physics-based forward simulation as well.
Cool. Thanks for the answers. Thank you.
Yeah,
Thank you for the talk. So just kind of a follow-up to the first question that was asked. Kind of like keeping in mind that the final goal is to be really robust to like long-tail scenarios and like maybe rare events. If you had to choose between like super high fidelity like image generated data or video data, and on the other end like the math-based data, what do you think is more like maybe like if you had to choose one, what would be the most promising route to achieving?
Yeah, so my answer is I don't think we have to choose one. I think we can choose both because I think we can start by training them in a separated fashion, right? If you have a modular stack, and this is kind of a little bit of the downside of a lot of modern stacks that they don't do that separation. But if you have a modular stack, you can actually train them separately, right? Even with BE models that works. Train them separately, use that initialization, and fine tune. That's actually the really big benefit of these modular stacks, right? If you need to do everything together, then compute will explode, right? That's ultimately the problem. So if I had to choose one, my answer is that I don't think we need to choose one. You can start with both, initialize one, but if I had to choose one, I would probably start with the scenarios because what we see is that you can use even relatively small planners can learn policies that if they're well conditioned enough that generalize surprisingly well. So that's a cool thing from an algorithmic point of view. So with relatively few parameters, you can actually handle a lot of conditions and have the same policy for all kinds of different agents, as long as you condition them well enough. So that seems to be a very exciting opportunity that's just a function of data. on the perception side, understanding the scene, that's more costly for sure.
Thank you.
Other questions? If not, maybe I would have a question regarding the realism of this adversarial agent behaviors that you mentioned. Like, how can we train them to not be too aggressive so that they resemble better maybe the real slight mistake that
Yeah.
driver would make?
Yeah, so I mean, the tilting allows you, the tilting is a control that you can essentially think of as a knob, right? Where you can sort of slowly change the behavior from non-adversarial to very adversarial, right? So that gives us a scale that we can play with. So that would be my main approach to solving that problem. Otherwise, you always are limited by the data distribution as well.
And I think that maybe if there are other questions, otherwise I have maybe a last one, John Hao. That's very interesting regarding the automated driving setting.